This is the tutorial for Chapter 7, Section 6, called Exponential Functions. So exponential functions are just another way to represent data. And so we've talked about linear functions before, and linear functions were when we drew a straight line. So that would end up being a linear function, and it had a parent graph of y equals x. And then we could always have the line steeper, where y would end up equaling maybe like 3x, or maybe not so steep, and it might be y equals maybe like 1/2 x. But then we could have it starting at a different point, which we call the y-intercept, and so maybe it started at positive 1 on the y-axis. And so that was a way to relate some data, and we also had quadratics that we'll learn about later on, a little bit more so, but we did talk about the general shape of a graph, which makes a U-shaped graph called a parabola. And those were in this form. This was the parent graph form that we looked at earlier, y equals x squared. Well, now we've got another type of function called an exponential function. And it's just another way to characterize data in different situations, and a lot of real-world situations have it, which we'll see today. So exponential functions are when we have a common ratio with the outputs, and we're going to end up seeing that. And since we have a common ratio, that output is going to change exponentially. So we're going to end up having the exponent being the unknown. That independent variable is going to end up being the unknown, which allows us to come up with a dependent variable. So we've got 4 different types of exponential functions that we're going to see. So we've got a y equals 2x. So whenever this number here, this number that changes values, so this basically means that we're doubling the values every time, we end up having an exponential function that looks like this. The general shape of the graph starts low on the left-hand side and exponentially gets a lot bigger as we go, as the x values get bigger. Where if it's a negative base number here, that means that the it's going to exponentially decrease. It's going to go down as the x values get bigger. We're going to end up seeing the outputs decrease quite a bit. Where here we have a fraction. Now they put parentheses around this to show that both values, the numerator and denominator, are both to that that exponent of x. And we'll see that this is a decreasing function. As the x values get bigger, our y values get smaller. And if it's negative, that means that it just does the opposite, as the y values end up increasing up to a certain point, but never get past this line, this x-axis in this case here. So we're going to see that where a represents the initial value, and we have b represents the amount it's changing by. The amount, like if something doubles every time, then this b value would equal 2. If it halves every time, if it decreases by 1/2 every time, so it decreases by 1/2 every time, then the b value would end up being 1/2. 1/2 would equal b. So it just depends on what that is, but a is always the initial amount. So if a substance started at 500 grams, then that would be your a value. And then if it decreased by a certain amount, that would be the b value. And x would represent maybe like time in this case here. And we get an output of amount that's left over. So let's take a look at some examples that we'll see. And so mainly what we're going to end up looking at is the graphs of these exponential functions. And so let's take a look at our first one. And before we get to the graphs, we're going to determine what is an exponential function. So we'll have some tables like this. And the main thing you're going to look for is your dependent or your independent variables. Those are increasing. These are increasing by 1 each time. So you see how they're going up by 1. So these are increasing by 1 every time. Okay, so we see that. But let's take a look at what's happening to the y values. Well, initially, okay, maybe it's going up by 6, but then when I look at this, oh, definitely not up by 6, so I got to change this. This would be wrong. So let's try another way. How else can we go from 3 to 9? Well, another way is to multiply by 3, and let's check if that's going to happen each time. Okay, 3 times 3 makes 9. 9 times 3, yeah, that makes 27. So yes, it is. It looks like it's going up by multiplying by 3 every time. So, and then 27 times 3 does make 81. So here we have a common ratio. So a common ratio is what we see on the outputs, and the inputs have a common difference. And so if we have that scenario where we have a common difference for the x values, a common ratio for the y values, that means it's an exponential. So this is exponential. And again, the reason is because exponential function, I'll say. And the reason is that the y values, or the dependent variable is, or the outputs, I'll say in this case, outputs have a common ratio, and the inputs, common ratio, and the inputs have a common difference. So that would be our reasoning in this case here. So let's take a look at this one. Let's see if it has the same scenario. I definitely see a common difference here. They're going up by 1 each time. Here, okay, well, it looks like we times by 3 like the last one. Let's see if that works out. Oh, not timesing by 3, because we went from 9 times 3 makes 27. So we've got to scratch that off and try something else. So when I go ahead and try another way to get up from 3 to 9, I might add 6. Well, let's see if that works with this one. 9 plus 6, yes, that does make 15. Let's continue that pattern. 15 and 6 do make 21. So we have a common difference again. So both input and output have a common difference. So the function is linear. So it's not exponential this time, it's linear because both have the common difference. So then you're going to see some problems like this, and what you're looking for is the exponent being the input, or the exponent being the independent variable. So we're going to say that this is an exponential function, exponential, and the reason is that the variable, we'll call it the independent variable, because we have two variables here. We have a dependent variable, the output, and the independent variable, the input. The independent variable is the exponent. And so that way I know it's going to be an exponential function, where this one is not exponential because the independent, we'll say it's actually a cubic function, is what I would call this, cubic function, because it's to the third power. Cubic function because the independent variable is to the third powers. Independent variable is not the exponent, we'll say. Is not the exponent. And looking at this one, this is another one. This is a linear function. Linear because it's got an exponent of 1. The exponent on the independent variable, exponent on x, I'll just say, is 1. And so it ends up being linear. So the way you're going to know it's exponential is when you see that exponent being the variable. There is another example of an exponential function. Exponential, and the reason is that we have that variable, the independent variable is the exponent. And so that's when you know it's an exponential function. Let's take a look at some other types of problems. Here we're going to end up having to graph some functions. And so the way I would end up graphing these is just using a table. And so I know this is an exponential function. Well, not only does it tell me, but I see that all of these have the exponent as the independent variable. So the way I'm going to set this up is I'm going to pick some independent variables, some values, some inputs, and then I'm going to come up with corresponding y values. And so I'm just going to pick these numbers, -1 to start with. And so what happens if I put a -1 here? Well, I end up getting 1/3, because when I go ahead and take the exponent, put a -1, I remember that we end up having to take the reciprocal of that number, to end up making it a positive exponent. And then I'm going to try 0. And I remember that anytime I've got 0 as an exponent, 3 to the 0 power is going to be 1. And then when I go ahead and plug in a 1, well, that's just going to end up making 3. I could plug in another number, 2, and you can really see how it increases. So if I plug in 2, I end up with 9. You can see that because, again, 3 to the first power is 3, 3 to the second power is 9, and even if I picked another one like 3, 3 to the third power is going to be 27. So those are some numbers. Now I can go ahead and plot them. So it looks like -1, I have to go up 1/3. So if I'm just going by ones, you can see how, okay, I go over one space to the left, up 1/3 of a space. So it's going to be right about there. Where if I go over 0, I go up 1, and over 1, I end up going up 3. Over 2, well, that's way up here at 9. So this is 5, 6, 7, 8, 9. Would be somewhere way up here. And so I can't even fit 27. So I've got an idea about what it looks like, though. So you see it's going to come over here, be really close to this y-axis. It's not going to, or x-axis. It's not going to go below it, though. It's never going to go below, but it's going to get really, really close. And then it's going to come up, and it's going to hit this point, come up, hit this point, and then really start to head uphill really fast. You can see that's the direction it's going to go. I'll put an arrow at the end showing that it goes on forever. Same thing here, arrow this way. Now it does not go below this x-axis, though. It ends up just getting really, really close, but never below, because you see when I have a negative exponent, it's not going to make a negative number. It's just going to make a fraction, and the fractions are going to be really small. So you can see how if I went ahead and go back to that picture that I had before, you can see that whenever we've got a number that's bigger than 1, it's going to make that exponential function like this. See how this one goes up? When it's 2 to the x power, it makes this red line right here. It's the same thing as the one that we just did. So you can see it makes the same sort of shape. It just goes up a little quicker. So on this one, though, it's 0.25. You see how 0.25 is between 0 and 1. So 0.25 is between these numbers. So when it's between those numbers, it's going to do something different. So let's take a look at it. So remember, 0.25 is like a quarter. It's the same thing as saying y to the 1/4 power, and then all to the x. So I'll go ahead and write that as well. And so I'm going to go ahead and plug in some numbers. We'll try -1 again and come up with an output. Well, remember, if you take a quarter and you go ahead and raise that to the negative first power, it's going to take the reciprocal. That's what happens every time. So I end up with 4. So it starts up higher. See, if I went with -2, I'll go ahead and put that in there. That would end up taking the reciprocal, and I'd end up with 16. See, 1/4 to the negative second power, I got to take the reciprocal and then do 4 squared. So you can see how high it goes up. If I plug in 0, well, I just get 1. If I plug in, because again, anything to the 0 power, no matter what it is always 1. If I plug in 1, well, I just get that same number, 1/4. If I plug in 2, I end up getting 1/16. You see, and as I get these numbers bigger, make bigger exponents like 2, 3, 4, it never makes a negative number. It always stays positive, but it makes the fraction very small. So let's try to plot this. Over 1 up 4 spaces puts me here. I can't fit over 2 up 16. It'd be way up here. Over 0 up 1, and then over 1 up 1/4. So it's going to be here. Over 2 up a 16th. It's going to be way down here. So you can see it's going to start up here, and it's going to continue down and get really, really close to this x-axis, but just never quite touch it. And it's going to continue up very quickly. And that matches what we had over here. You see, when it was, let's go back to that, when it is a fraction as this number, that the base number, we end up seeing that when it's a positive fraction, we end up seeing that number, the y values get really small as our x values get bigger. That happened with our problem as well. So here we have a negative number, -1.2. Well, it is a number that is negative, but it's also, if we take the absolute value of it, it is greater greater than 1. Okay, so the absolute value is greater than 1. So we've got an idea about what it might look like if we look back at that chart. But before we do that, let's go ahead and see what happens when we plug in some numbers. So remember, you're taking the exponent first, then doing the opposite. So if I plug in a negative number, like let's try negative 2. Now it's 1.2, so it's like 12, which makes 144, but then it moves the decimal 2 spaces over. So it makes 1.44, and that's going to end up being negative because I take the opposite of that number. And so 1.44 negative. And then if I plug in a negative 1, well, it just gives me the same number, negative 1.2. And then if I plug in 0, well, I get 1, but then I have to take its opposite, and that's why it's negative 1. If I plug in positive 1, hey, I get the 1. Let's see here, can fix this one here because I had a negative number and I forgot to take the reciprocal of those because I was doing negatives. So let me fix that real quick. So I'll go ahead and fix what I had done over here. So what I ended up making a mistake on this part with is that when I have the negative number, I need to take the reciprocal. So I need to take the reciprocal of that 1.44 and the 1.2. So let's go ahead and do that. When I take the reciprocal of 1 over 1.44, what that ends up being, if I go ahead and do that division, it ends up giving me 0.69. About that. The 4 ends up repeating at the end. And then I'll do the same thing with the next one. I'll take 1.2 and take its reciprocal, and that gives me 5/6, which is 0.83. So negative 0.83 repeating. And then I end up with negative 1. 1 would end up putting me at 1.2. Negative, though, because it's the opposite. 2 would end up being negative 1.44. So let's see what this looks like. So I'll start down over at, let's see, at negative 2, and I end up going down 0.6944, so it's going to be somewhere right around in this region here. And then I go to negative 1 over, I go 0.83, so about right there, and at negative 0, I just go down to negative 1. Negative, or 1 space over, is going to be 1.2 down, and 2 over 1.44. So you can see how when it's really close to, it's not going down, it's taking a little bit more time to get there. And the reason is that it's pretty close to 1. So when it's close to 1, it's not going to change so quickly. But when it is not, when it's a little bit further from 1, you see how much more it changes as we go. And it does kind of match what we had over here. So if we go back, we can see that it was a number that was absolute value was bigger than 1, and it does kind of form the shape where it gets really close. As the y values get bigger, the x values get smaller. As the y values get smaller, x values get bigger. It's kind of the same shape we end up having over here. So those are the types of problems you're going to see on tonight's homework. Good luck.